right. Hello, everyone. Thanks for coming to my talk. So I'm glad to talk about this recent work on dynamic matching refugee resettlement, which is a joint work with a fantastic lineup of co-authors, Kirk Bansak at UC Berkeley, Soonbong and Vahideh Manshadi at the Yale School of Management, and Elisabeth Paulson at Harvard Business School. I'm happy to announce that I finally found a way, as an Iranian, to show Persian poems on my slides. And I just wanted to point out to the last two sentences. It's by Saadi Shirazi from 13th century. So if you have no sympathy for human pain, the name of human you can't retain. And that brings me to the main topic I'm going to talk about, which is really an international human crisis we are dealing with. So as I'm giving this talk, we have around 35 million refugees around the globe. And if you're wondering where they're coming from, we have huge number of the refugees coming from Syria. Then we have Ukraine, Venezuela. So it's kind of a rank list. And recently, because of the, so we have from Afghanistan, and then recently because of the conflict in Gaza, we have a huge number of Palestinian refugees, and these numbers are only going up. So there is really no sign of things getting better. And then what's the solution? There is an international effort called Refugee Resettlement, which is really trying to find a durable solution for this human crisis. And the idea is that we try to first identify these vulnerable communities that are displaced, they have no home to return, and then relocate them to a new host country, and eventually find them a new home and a new job. So this process is supervised by a UN agency, UNHCR, United Nations High Commissioner for Refugees. And UNHCR works in collaboration with host countries. Actually, my country is on top of the list in terms of the number of refugees that they admit, but they don't do a really good job at resettling them. And then somewhere down the list, ranked number 11, is US, which is the main subject of my talk. So in the United States, I'm sorry, something weird happened. Yeah, so in the United States, there's this program called USRAP, United States Refugee Admission Program. And the main goal of this program is basically delegating the task of resettlement across different agencies. And hopefully we can find a new home and new job for these individuals. And let me zoom a little bit about these operations. So there are 3 federal agencies involved. In particular, we have USCIS. If you're living in the US and you have applied for visas, you probably heard the name of this organization. I'm sorry, I don't know why this is constantly happening. Right. So USCIS is part of the Department of Homeland Security in collaboration with Populations, Refugees, and Migration, which is part of US Department of State and US Department of Health and Human Services. They basically go through the cases that are being referred by UNHCR to the United States, and then they try to figure out which of them they should be admitted. And then they work with 10 national agencies. One of them is our partner. So we work with Global Refuge, formerly known as LIRS. And these agencies, they really try to do the resettlement process. And let me zoom into actually the problem that an agency like our partner should solve. All right. Okay. All right. So you should imagine that these cases arrive on a weekly basis. Basically, these cases, they have been waiting in the federal pool for some time, somewhere between 14 to 24 months. And upon their admission to US soil, they are going to be picked up by, maybe actually I can use the keyboard. That's going to be easier. Yeah, so they're going to be picked up by someone from the agency, which is going to provide them with basic needs and temporary housing for some time. And then eventually are going to assign them to one of their affiliate localities. So these are basically different offices that the agency is working with across different states in the US. Imagine, for example, our partner agency has one office in almost every single state in the United States. And these service providers are provided what I call the post-allocation services. You should really think of them as service providers that help these individuals to find a job. So they assist them with job search, provide vocational services, sometimes translations, etc. And this is going to basically help them to find a job. So if you're wondering why this is a kind of an important problem, there are studies that show this initial matching has immense impact on the final outcome. In particular, if you look at whether these individuals, they can manage to find a job, especially in the next 3 months, because that's kind of an integration metric that agencies are going to be evaluated based on, it turns out that these initial matchings are quite important. So this brings us to this mission. So we are trying to design, I'm going to focus on 2 words, data-driven and dynamic assignment algorithms in order to maximize the employment outcome in this context. So basically, we are playing the role of the agency. We try to design an algorithm that makes these assignment decisions, where to send these cases. And now, so this task has 2 steps. So the first one is somehow you want to use prediction models, say machine learning models that based on historical data, they can predict the employment outcome probabilities. What does that mean? So if I send a particular case to a location, what's the probability that that case can eventually find a job in that location? But once you have these prediction models, which our partner agency already had, they had these in-home machine learning models thanks to their previous collaboration with the Stanford Immigration Policy Lab through this project called GeoMatch. The next question is how to actually recommend these cases to different locations. And that's where our paper sits. So it's basically coming up with an algorithm that can recommend a location via some sort of dynamic learning and optimization, which I'm going to explain soon. And our task was really like redesigning the algorithm that they were already using. Okay? So this is kind of a challenging problem. Let me try to tell you a little bit about some of the operational intricacies that this particular problem has. So first of all, in terms of timeline and scale, so we're really thinking about a planning horizon of a year. Think of a fiscal year starting from 1 October to the next October. So for example, 2022, our partner had around 5,000 cases, and they had to be matched to 45 affiliates. They almost have 1 affiliate location in every single state. Now, these affiliate locations, they have what I call annual quotas. So in fact, there are annual quotas set by Congress. And then our partner agency, based on this number, decides on certain soft capacity constraint on each of these locations. And one goal of the matching algorithm is trying to respect these soft capacity constraints to the extent that we can. At the same time, you should really think of service providers that are sitting in these locations. Our partner agency in particular was pretty much underemployed, especially when it comes to special services, for example, Farsi translation. They don't have enough workforce, so that makes it kind of a first order in this application that you want to make sure these service providers are not congested, because then you're going to create huge backlogs, and this entire system is not going to function as it expects to function. And the last one, in fact, we have reliable data for predicting employment outcomes, but when it comes to the arrival process of these refugees throughout the year, in fact, it turns out that the historical data is very misspecified. In fact, when you look at the data of our partner agency, the composition of cases from 1 year to another changes a lot, because it really depends on the wars that are happening right now in the world, like all these crazy countries that force these individuals to leave their countries. This thing changes from 1 year to another. So one of our goals was really like thinking about an approach that is prior-free, doesn't really rely on historical data. And let me zoom in a little bit about this aspect. In the context of United States, there is this regulation called family reunification. So in particular, if you are a refugee or a refugee household, and you self-declare that you have a family or friend somewhere in the United States, this system should be assigned you to the same location. In some sense, this is kind of what I call a quote-unquote tight case. And now you look at our data, and different affiliate localities. So the x-axis are the indices of these affiliate locations, and on the y-axis, I'm showing the number of tight cases for that location throughout different years. And you see from 1 year to another, these numbers, they fluctuate a lot. It's kind of like indicating that the composition of cases is changing. And not only about the tight cases, in fact, if you look at the rest of the cases, free cases, still you see a huge amount of discrepancies between the data from 1 year to another. Right, so long story short, we are asking this following informal research question. How can we design a dynamic matching algorithm that optimizes for employment outcome while addressing these particular operational limitations? So in particular, we want to have an algorithm that doesn't rely on historical data because they are potentially misspecified, and instead tries to learn and optimize over the span of a year, basically trying to picking up the arrival pattern of the arrivals of these refugees throughout the year, and based on that, make the assignment decisions. Second, we want to avoid overburdening our affiliates. And now, from the perspective of an affiliate, we basically have two types of resources. On one hand, there are these quota constraints. Think of it as some sort of a static resource that it's a capacity constraint. You should not violate that to the extent that you can. Because of the tight cases, there is no way you can avoid over-allocation, but you're trying to minimize over-allocation as much as possible. And then there is this dynamic resource, which really is avoiding congestion. So you try to use the service providers in an efficient way to avoid congestion of service backlogs. Okay? And I should say that on the technical level, the handling dynamic resource is actually the main technical contribution and novelty of our paper. And I'm pretty much excited about this aspect because I'm sure it has other applications in other domains. So let me try to make everything a little bit more formal by first introducing a model. So basically how I think of this problem. Say we have n affiliate localities at different locations in the US, and then T cases are going to arrive throughout the year. Now, each affiliate location has a capacity constraint. I'm denoting capacities by CI. And let's normalize them by the length of the horizon. So we have these parameters rho I, and CI is essentially equal to rho I times T. And then for each of these locations, we have a queue that provides post-allocation services. So there is a service at a certain rate. For QI, the service rate is going to be proportional to the capacity because that's how you set up these systems so that the queues don't explode. The service rate is going to be rho I. It might have some slack, and I'm going to denote that by epsilon. And we make this assumption that the summation of rho I is equal to 1. So if you are familiar with these types of models, this is essentially a supply-demand balance type assumption. Now, I'm going to study this model in different regimes, so in particular the stable regime where epsilon is a constant. You can think of the critical regime, that's the other side of the spectrum where epsilon is 0. You can also think of the near critical regime where epsilon is tiny. In particular, it is little or 1 over square root of t. And now here's what happens. So cases arrive one by one. I'm simplifying, so in reality, you will have batches of cases that arrive every week. But for the purpose of this talk, just assume that one case arrives every week. So we have these cases arriving. And if I look at one particular week T, so this case arrives. You don't know which cases are going to arrive in the future. But upon arrival of case T, you observe its type. And the type encodes a bunch of information about this case. So in particular, there is this vector WT, which encodes the employment outcome probability. So WTI is the probability of getting a job if you assign refugee arriving at time T to location I. Yes? Is
the employment outcome orthogonal to the congestion?
It is, right. So basically, this congestion, I'm going to explain. So these employment outcomes are going to impact your matching decisions. And the arrival process of these queues are endogenous to the matching algorithm. So in that sense, they're connected, but not directly. Good question. So if the case is a free case, that means it can be assigned to any location, then it is encoded in the type. But you might also have tight cases that are tied to a certain location. And in those cases, the matching algorithm has nothing to say. So you have to just assign that case to that location. You should really think of it as part of traffic that adds these shocks to different locations at certain rates. Now a matching decision is going to be made. For example, let's say you decide to send this case to a location. You have to use 1 unit of your static resource, this capacity constraint. The case is going to be added to the end of the queue. And then the service is going to happen. So in order to model this discrete queuing system, we are thinking about Bernoulli random variables that are going to realize after allocation. So if you have a 1, that means the service is going to happen at that discrete point in time, otherwise there will be a 0. So if there is a service, the queues are going to advance, otherwise they're going to remain at their previous state. So just as a recap, so when you think about one particular queue, this backlog stochastic process, it follows the following dynamics. So backlog of location I at time t plus 1 is essentially the positive part of the previous backlog plus potential arrival minus the service. It's a stochastic process that has endogenous arrival, and that's endogenous to the decisions of the matching algorithm. All right? So now, let's for a second assume that we know all the cases that arrive throughout the year. Then you can write down an optimization problem with a mixed objective that basically targets towards the requirements of our partner agency. So the objective function we are trying to maximize in this problem is a mixture of the total expected outcome, basically the expected number of jobs that this assignment will create at the end of the year, minus some scalar, alpha times the amount of our allocation, minus another scalar times the average backlog of all these queues. All right? So we try to basically maximize the employment outcome while minimizing our allocation and also keeping the backlog short. And at the same time, we are going to make sure that no free case is going to cause overallocation. So tight cases can cause overallocation, but when you're matching a free case, if you don't have capacity, you're not going to use that capacity. So this is basically kind of like the setup. But you have to solve this problem in an online fashion. So these cases arrive over time. So our benchmark is what I call the optimal offline. This is basically the solution of this stochastic optimization problem in expectation. And then I'm going to evaluate the algorithms in terms of their regret, which is the difference between optimum offline and what my algorithm obtains. And that brings me to my main results. So we basically designed a near-optimal distribution-free primal dual dynamic matching algorithm. We actually have two algorithms in the paper. They follow two categories of design. The congestion-aware design, where the algorithm observes the backlogs and based on that, make the matching decisions. And we have the congestion-oblivious algorithms that without even backlog information, without knowing how long are these queues, they can make a decision. And on one hand, basically at a high level, so the technique is trying to learn the shadow prices dual variables corresponding to both the static resources and dynamic resources, with the caveat that dynamic resources are going to introduce too many dual variables. So it is really hard to learn, but it turns out that you really don't need to learn them. You can estimate them by observing the length of these queues, and they are proxies to really like these complicated dual variables. The other algorithm is really like trying to keep the drift of the stochastic process, the backlog of stochastic process negative. And the way to do that, it turns out that lies in the some sort of last iterate convergence, high probability last iterate convergence for the learning algorithm that's trying to learn the shadow prices. And we use a kind of cool trick by changing the learning rate. We managed to obtain this kind of high probability last iterate convergences. On the practical side, we actually proposed this algorithm to our partner, which is a more efficient, distribution-free, and in some sense, much less computationally demanding algorithm compared to their status quo algorithm and also the other algorithm they were considering. And so let me just skip these theoretical results, but the high level is that the algorithms, they have information theoretically tight regret bounds. And there is actually a gap between the congestion-aware and congestion-oblivious when you go beyond the stable regime and you get close to the critical or near-critical regime. But in the stable regime, the two algorithms perform pretty much with the same order of regret. And let me tell you very quickly what the algorithm looked like. So I'm going to start with the optimization problem. So we are going to follow a primal dual recipe. So basically trying to look at the dual of this optimization problem, introducing proper dual variables corresponding to our constraints, there's convex terms in the objective by applying functional duality, and then you can basically write down a dual problem. And the good thing about the dual problem is if you magically know the optimal solution to the dual, then you know what the right algorithm should look like. In particular, if you manage to solve the dual problem and you know all the optimal dual solutions, in particular these lambda i's, beta ti's, theta i's, then this is what you should do. When the case arrives, you have to adjust the weights based on the dual information. As you see here, you basically need to subtract a bunch of dual variables from the employment outcome probabilities, and you have to match the case to the location that has the best adjusted weights. And this is going to be essentially following optimum offline. But the catch is you don't know these dual variables, and you have to learn them. And you look at these dual variables, the thing that makes this problem challenging is that one category of dual variables are corresponding to the backlog dynamics. You have too many of those dual variables, which makes learning them really hard. So what we do in the paper is we study a surrogate dual problem, which in the interest of time I'm not going to talk about. And it turns out that if you follow the primal dual recipe in that surrogate dual, which is a relaxation to the current dual problem, then you can basically learn some surrogate dual variable that turns out to be just a scaled version of the backlog itself. So you can use the backlog information as some proxy for that dual variable. And when you use this technique, you end up with generating negative drift in all of the backlogs, and therefore you can control these stability of these queues. This is what the final algorithm would look like. When a case arrives, it is a tied case. I'm just going to match it to the target affiliate. If it is a free case, we are going to assign it to the affiliate with the maximum adjusted weight, where you have dual variables that you are learning by using some online learning algorithm, maybe your favorite online mirror descent. I'm using exponential weights in my slides. And then for the dynamic resource, we essentially use a scale version of the backlog. And it turns out that this will do the right thing, and you can obtain the regret bounds in the paper. So the analysis is actually quite involved. It is using ideas from learning in games with Lyapunov optimization. In the interest of time, I'm just going to mention these names in case that you're interested. I'm happy to talk about it offline. We worked with our partner, and we ran these algorithms on their data, and it turns out that both in terms of employment outcomes and over-allocation and also average backlog, we basically beat the status quo and the other proposal based on access to historical data. I think one thing that was going wrong with the other proposal was the assumption that you have access to the historical data, which wasn't really like the case. All right. So let me wrap up. Thank you so much for your attention. And in the interest of time, let me just take the questions offline, I guess. I'm happy to take questions if I have time.
I think we're a bit tight on the time,
All right.
sorry. But let's give a round of applause for Rad.